So there will be a homework assigned later today for the Friday. Okay. Okay. So we're doing the partial derivatives. So we could do some more partial differentiation, but that will go through the rest of the course anyway. So little by little we'll get there. Doing by differentiation by hand. So we just at this point we do visualization of the partial derivatives, and this is the example that we looked at. Let me maybe. So I want to construct partial derivatives of this function, the ones that we found last time, analytical. Okay, so it was like x y cosine xy and x cosine xy. Those were the two derivatives. This is sine xy. Okay, you can see the sine behavior here, or there, everywhere pretty much. And now we want to construct its partial derivative. So there will be two more pictures just like that. Not like that, but similar. Okay, so we already know how to do it. We did it with the with tables. Remember that if you're writing from tables, you go to the next element and you compute you go horizontally for x, not like here. Here x is vertical. You go x horizontally, and then you look at the change of z. These are z's, and divide by the change of x. The change of x or y is right there in the corner anyway, so it's the same value. Okay, so let me make it slightly smaller so it would fit. So I'll do this. Okay, so I will be producing here a similar table to the left, to the right of it. What happened to the? Oh, I cut a little bit. Okay, I cut a little bit of the graph of the. Okay, so this is the data. Okay, so it's cut a little bit, but you still can recognize the waves of in both the directions. Even though if you go diagonal, it's still a wave, right? If you go like this. Okay, so all right. So this is what I'm going to do. So this will be okay. First of all, let's say this is just right. F equal sine xy. So that is my function. And what I'm going to put here in a similar place will be f prime x. Okay, so that's the alternative notation for the partial derivative with respect to x. So once again, just like in calculus 1, there are two main notations for the derivatives: the Lagrange notation with primes and the Leibniz notation, which has those d's. Okay, so let's do this. Okay, so I'll just write here the let's say everything is equal to this one. Okay, and then I'll just spread it. Enough. No. Okay. So these are the same values for the time being. But all I want to do is just too many. Yeah, sorry about that. Let me erase these words. Okay, so I have my x's and I have my y's. So these are my y's. No, these are my x's. Y's are at the top. So let me add that. Okay. x's and y's. Okay. Okay, so now I have to carefully, okay, well, step number one, remember that we'll have less data. We'll have less data because there are fewer intros than the points. So these are the points, the 20 by 20 roughly points, and this will be, but there will be nothing here, and there will be nothing there. And this is actually extra. Okay? So, okay, so what do I put here? So it is a change of x of what we see in the left-hand side. So let's just concentrate on one entry. So it is, it will be, I will be going from, I will be going vertically, okay, and I will be dividing by delta x. So I will looking at these two. Okay, so this is the change of x vertically, and it will be divided by h, which is on the left, 0.1. Okay, so this is the this is what this entry is supposed to be. So I take this. Okay, so it gives me the value, the correct value, but now I have to subtract and then divide by h. Okay, so let me put. This is really tiny, unfortunately. And I will subtract this one. Okay, and divide by, once again, as always, row 2C1. Row 2C1. Okay, so only one entry right now, but I got it. The rate of change. Well, that's, why is it 0.1? Oh, well, why not? It could be 0.1 just as well. So let's confirm. So once again, I'm looking at this entry. The change of x is 0.1, while the change of z is 100, 0.01. So 0.01 divided by 0.1 gives me 0.1, right? Yeah, that works out. Okay, so let's get the rest of them. Okay, so once again, filling in. Okay, let's see what it looks like. So just take this one and put it here somewhere. Okay, so now I have to choose the data correctly, like this. Okay, that is the partial derivative. Okay, let's confirm. Let's confirm that it makes sense. Okay, so let's concentrate on that corner. Well, there's a corner over there, and we have two partial derivatives. Seemingly, what do we say about those two partial derivatives at the very corner? What?
Zero.
They could be actually zero, but at the very point, yes, it is zero, it appears to be. But if you step off a little bit, they become positive, right? There's a growth in both directions, in x direction and the y direction, it appears. Okay, so if we look at, well, actually we don't care about both directions, we can only care about the x direction, which is red, and, well, actually, I'm wrong, there is no change. Along the x-axis, the value is 0, so the derivative should be 0. The product should be 0 on this location. And indeed, well, it is. Well, we don't have this data, but a little bit. You step off a little bit, and we have about the derivative, the partial derivative with respect to x is 0 on the y-axis. On the x-axis, that is where the y is equal to 0. Okay, so once again, as you can see, this thing is equal to 0. On the x-axis. On the x-axis, y is equal to 0. Okay, so we can do that, and otherwise, if we start off moving off of the x-axis. The derivative initially appears to be positive. This is, I think, this is the line where the rest of one is above the xy plane, and this part over here is below the xy plane. Okay, so it starts off as positive, and indeed we can see the growth over there. Either you start this way or that way, you have the growth, and that is the so far matches what we've got. Okay, so let's do the same with the other one. So meaning I will have f prime x, f prime y. Okay, so over here I have f prime y. Okay, so once again I'll do the same thing. So this is equal to this value over here. Let me start right here. Over here, equal to this value. Okay, and then we are spreading like this. Okay, so well, there's a little bit of once again too many borders. Okay, so right border and the bottom border. Okay, so these are the x's and y's. This is still not the what we want. I delete one row, one column as things that we cannot use, and now I'm going horizontally because the y-axis is horizontal. So I will be able to put anything over here. I will be subtracting. I will be looking at these two values. Okay, these two values will have to be subtracted and divided by h. Okay, so let's carry that out. Okay, so over here, this one is equal to parentheses minus this horizontally, parentheses divided by R2C1H. Okay, so that is my value. The rest of the values are acquired from it by copying. Okay, now we will try to create a chart. Okay, the right data is here, so let me take it and put it in the right spot here. And well, doesn't match exactly. Okay, so at the edge there's some trouble here, but that's not a big deal. I delete it. Okay, one more time. Okay, okay, okay. So you can see how it matches, right? Our formula. You see the match? What is this?
X equals, or y equals 0?
Y equals 0. Y equals, x equals 0. This is the y-axis, so this is the second line that I have over here. Okay, so equal to 0 on the y-axis. That's where x equal to 0. Okay, and then as we start off, moving in the direction. This original function is still in the middle. The two partial derivatives are on the right, these two. And as we move away from this axis, the derivative is positive, and once again, at some point, this is the cutting edge. It becomes negative. Okay, so partial derivatives, it would be pretty hard to actually figure out the way point by point to figure out to recover the original function, which is incidentally what's the name of it? How do we what's the name of how we recover the original function from its derivative? Integration and then differentiation. Yeah. So we still want that. We still want that, right? So every time you solve a problem such as differentiation, there will be a problem when it requires you to go backwards and figure out where the function came from. Okay. So it is possible to hypothetically to take these two functions and recover the function over there. Okay, so just knowing the derivatives according to partial derivatives, you know that how much you're going to grow if you go along the x-axis. Along the axis, you'll get those. You'll build in just like integration in calculus 1. So you do it with respect to x, and except you do it many times, and then you have a bunch of curves that you build by differentiation from those functions. You'll have roughly this picture, or you can do it the other way around and do it along the y-axis. Okay, you need both of them. So the true illustration, however, of the second of the two the two partial derivatives would be to put them together as follows, which we did a little bit of that already, and that is to put them together in one vector, which is called the gradient. So this is a new kind of function. This is a new kind of function because it is certainly not a parametric curve. This is not a function of two variables. We know it is actually two functions of two variables. Okay, so the function that has input, this one, what we have on the right, it has as the input has two numbers, x and y, and then it has output is also two numbers. Okay. So this is called a vector field, and just quickly to illustrate what vector fields look like, and even though it might be pretty hard to imagine how you're going to make anything from these two graphs, but actually all you have to do is just pair up corresponding entries. So I will pair up this entry with that entry. So partial derivative with respect to x and partial derivative with respect to y at the same location. They're taken together, and they will form a vector with components 0.1 and 0.1. And that vector, as you might remember, indicates the, what does it indicate? The direction of the fastest growth. Okay, so for example, if we are here somewhere, right here, the fastest growth is roughly 45 degrees. Well, you can guess it because the function is symmetric to begin with. So x and y's are fully balanced. So the fastest direction will be 45 degrees. And even if you keep moving away from zero, the fastest way to climb would be in the direction of 45 degrees. Okay, so you can probably, by looking at this picture on the left, you can probably guess that. To make clear, I'm still looking for a way to do the three-dimensional rotation, and I still can't find it. So you could rotate that. Here it is, 3D rotation. Okay, so it gives you just a better picture of the whole thing. Okay, so this, if you want to look at it slightly from above, and this is the 45-degree growth. Okay, which will give you the best one, the fastest one. So if you're climbing, you want to get to the hill, to the top of the hill as fast as possible. That's how you do it. So this is the other angle. Okay, so once again, if we start over here, which way do we climb? We climb this way. You know roughly the rate of change in the steepness of the the steepness of the graph of this function. If you go this way along the x-axis or along the y-axis, it will be, in either case, it is 0. So which way do you go? You go actually at 45 degrees. Okay, even though it's initially it's still 0. You have to actually, with this function, you have to step off a little bit off the x and y axis to actually recognize that there is some growth. Otherwise, it appears to be flat. So only. Well, actually, a question for you. So, what do you do if the derivative is equal to 0? Which way? How do you know which way to go if you want to climb as fast as possible?
If both are 0?
Yeah.
Would it not matter? I mean, every direction is.
No, not necessarily.
Would you consider a neighborhood around that point?
Yeah, but then you have to step off it. So think about x squared. Okay, so the derivative is 0. Take x cubed. And it matters which way you go. You go to the right, you're climbing. You go to the left, you're going down. So it matters. Well, actually, this is a bad example. A good example is, what is a good example? X squared is a good example, I suppose, yes. But the point is that the good example is a saddle point. A saddle point, and so it has, you know what a saddle looks like. It has two, there's a room for your legs, and then there's room for, and this is the head and the tail of the horse roughly. Okay, so that's what it roughly looks like. Okay, so what is so special about this point over here? It is both partial derivatives are equal to 0, but there's a choice. You can go this way, you can go that way, you can go up or down. So look at how do we determine which one to choose? Both derivatives are equal to 0. The second derivative, because you'll know the concavity, right? So you choose the one with concave up and follow that direction. If you have the second derivative available, then it will tell you the positive second derivative will give you the growth, and the negative will give you the decrease. Okay, so that is roughly what you could do here if you take either if you don't have that as an option to stepping up. Doesn't matter how little you step off to look at the slope, and you'll know which way to go. You just proceed with the gradient. Okay, so in this particular case, I think I rotated pretty well, and you can see how there's some growth first off a two horizontal line. There's some growth. There is a tip over there somewhere in the middle, which would be, you can guess what that special point is and how to find it by what is so special about the tip of the hill.
It's a local maximum?
It is a local maximum, but once again, invoking the ideas from calculus 1, how do we use the derivatives?
Derivative is 0.
What?
Derivative is 0.
The derivatives are, the partial derivatives are equal to 0. Always the same caveat, again, from calculus 1 is you have to, the word that I have used up until now is the word is differentiability, because the function is not differentiable, that these ideas don't work. And even then, once again, another idea from calculus 1, where is it? Derivatives are equal to 0. Remember that example in calculus 1, derivative equal to 0 does not mean that you have a maximum. Remember, it's called the first derivative test, which fails when, which might fail, which goes only one way. So if you have a maximum, that derivative equal to 0 under differentiability conditions. But even though you have derivative equal to 0, it does not prove that you have a maximum. Okay, that's exactly the story from calculus 1, except this is more complicated because you have two derivatives to worry about. And then the question of differentiability becomes more complicated, because just because the partial derivatives exist doesn't mean that everything works out, because the partial derivatives will only test your surface in the two directions. What if you go diagonal and there is some kind of cliff there? And once again, this first derivative test fails. Okay, so let me, what time is left, try to elaborate on this idea of this discussion. Remember, I tried to do discussing the the parametric curves and functions of two variables side by side. Remember that example of prices of bread and prices of sugar and wheat as depending on time. That's the parametric curve on the plane versus the price of bread as it depends on the prices of sugar and wheat. And that combines together, so that's the second part. The first part is the parametric curve. And you certainly can, that's the example I intentionally picked, so that we would not fully devote ourselves to the space of, to the physical space. So So we would not be limiting ourselves to dimension 2 or 3, or it would be high. But ultimately, we have to come back, and we will all the time. The best metaphor for a parametric curve is a path of a moving particle. Okay. So parametric curve. So it's a path, the path of a moving particle. On the plane. Or particle, or any other path. So it doesn't have to be a particle, really. Moving object. Okay, so the example that I want you to come back every time you don't understand something about parametric curves, go to motion. Okay, and then the path that you see it will be a parametric curve. Similarly, if we're talking about functions of two variables, the metaphor for instance of its existence in the real life is terrain. Okay, or relief, or just a map of elevation. Okay, so these two actually can be combined together if we just forget for a moment about particles, and just if we could just speak about map and a trip that you start by you plan your trip with a map. This is your map. And a map might contain, the simplest map contains things such as forests and rivers, but it does not necessarily contain elevation. Okay, so that will be the second map, is not, or not a map, or real deal. There are hills like this. Okay, so this is my parametric curve. Will look like this. We are taking a trip through wilderness, and we design a trip. We go this way. We know how far, so we have distances here, but only horizontal. How far we move horizontally is part of this trip. And now on this separate, totally separate, now if we want to take it to the next level, our planning, we include the map of elevation. Okay, and so we put these two together in order to discover how much we're gonna need to climb. So how do I do it? I somehow have to find this path which is on the horizontal plane. Horizontal like this, meaning meaning what? So meaning that this is east and this is north. Okay, so east and north, and this is similar here. This is east and north. But they have to be matched in order to us to discover how much we have to climb. So this is only give you how much distance we cover horizontally, as if there is no terrain. And if we need to know how much we actually need in energy in order to complete the trip, so somehow I have to find this map on the. This is how I do. I take that map and put it like here. Okay, so I take my map with my curve already plotted. Okay, and then what I do is I find elevations like this. That's what we have discussed. It is the composition. Composition of, on one hand, our parametric curve, so our trip, our location is the location on the map, two numbers. As a function of time, that's how you plan the trip roughly, where you're going to be, where and when you're going to be. And then if you want to, in addition to know how far you get up, you compose that function, your trip map, with, as a function of time, with two function of two variables which represents the elevation. Okay, so that's what we did. We can do, and then what becomes crucial is now how do derivatives come into play, and you can guess what. Well, let's try to investigate that. So the question that we want to answer is how fast do we climb at any particular moment. Suppose we pick a particular moment and we know how fast we're moving along in the horizontal direction, and now in addition we want to know how fast we're climbing. So how do we figure that out? I could do the composition. The point is, can we do it by looking at the derivatives of these two functions only? So in other words, express this number in terms of number one, how fast we're moving horizontally, and number two, how steep is the terrain. Okay? You realize that these numbers, these two questions simply express, or all three questions actually, express the same thing. We're talking about the rate of change, we're talking about steepness, speed, all of these, it's all about derivatives. Okay, so the question looks more complicated than it actually deserves, because you can have the almost identical story entirely within calculus 1. So imagine that you are not moving, your motion is entirely west to east, like this. You're moving that way, okay? Then these y direction doesn't matter, and what we have two functions here. How fast you move horizontally as a function of time, and here you have the elevation of your terrain. Two functions, and we compose them together, and now you are talking about the derivative of the composition in terms of the derivatives of those two functions. Okay, so you know what the answer is.
Chain rule.
What?
The chain rule?
The chain rule, in other words, you multiply them, right, by the chain rule. So multiply them, these two, in order to answer this question. Okay, how fast we climb. So you multiply your speed, the horizontal speed, by the steepness of your terrain. Okay, so imagine that even forget about the chain rule. You can just use your common sense to answer the question. Why do we end up multiplying? Well, you can imagine that. Suppose I'm moving horizontally at some speed. If I double my speed, what's going to happen to the rate of climb? It also doubles, right? Similarly, what if I keep my horizontal speed the same, but now I double the steepness of the terrain? How fast? How does it affect the steepness of my speed of my climb? And one doubles again. Okay, so that proves that this thing is proportional to those two. Okay, and that's why we multiply them. That explains the chain rule, why it is applicable. And the only thing that remains here, a big part of this course, is to figure out how is that we're supposed to multiply those derivatives. So because the derivative of a parameter curve is another parameter curve, and at every location it is a little vector. And on the other hand, as we just established, the gradient of the derivative of the terrain, of the function of the terrain, is the gradient, which is also a vector. So you have two vectors, and we will have to learn how to multiply them in order to produce nothing but a single number, because ultimately this function is a function of one variable. Okay, let me I think I have another illustration of this process here. Yeah, here it is. Okay, so map, I'm taking the functions that I've seen already. I'm just doing it again. Okay, so suppose, once again, this is like we in the beginning of our trip. This is our map, and this is how we move through the map. Okay, with time marked. This is the path, and we know when we're going to be at each location. That is the terrain. Okay, and now we combine them together, compose, in order to see what the elevation. This is how the composition happens from moving from left to right. So I put the my map under the map of the terrain, and then every time at every location I'm looking how far I have to be in order to how far is the elevation when I am located in this particular place. So for example, if I'm right here, if I'm here, this is how far high I am. And if I'm here, this is how far. At the end, as you can see, the elevation is insignificant. And then at the end of when we carry out this composition all the way through, this is the end result. Well, that's not the one. Here it is. And then the composition gives me a function of time, which appears to be fairly constant elevation in the beginning, and then it goes down. Okay, that's roughly what we see in the previous picture, this picture, right? So we start high and then we go low. But the end result is elevation as a function of time. And then if we differentiate, we need to differentiate, we differentiate. Okay, so, all right. So I'll try to sort this out. I'll assign homework later today, and we're going to start on the next big topic being the multidimensional spaces.